Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of dandelion images. What it really is images of grass, and some of them contain dandelions and some don't. So we're going to try to predict whether or not there's a dandelion in a given image, and I'm going to use a pre-trained transfer learning model today. I'll just use MobileNet again because it's faster to train. It's better for the purposes of these videos. So we have a pretty even class distribution. Not much of a class imbalance, so we shouldn't have too much of a problem. So basically, yeah. So we're going to train the convolutional part of the. Sorry, we're going to download the convolutional aspect of the neural network using Keras, and then we'll build the classifier after the CNN has extracted the features we want. Let's hop into the notebook, and we're going to import NumPy and pandas for working with the data, along with the path object from pathlib and os.path. I'm actually going to turn on GPU acceleration since this is an image classification task. There we go. GPU, turn on. For pre-processing, we're going to use the train test split function and the image data generator from keras.preprocessing.image. And we're going to use TensorFlow to build a model, and for evaluating it, we'll just use the accuracy score and F1 score from sklearn. So let's go ahead and import all of that, and I'm going to load in the data just by specifying the file path to the images. So the file path I want is the path to this folder that contains the class folders. So we copy that, and I'll call this image_dir, and there it is. Now, because there's no a built-in train test split in the directory tree, we're going to use flow from data frame, which is a function from the image data generator, which will allow us to basically flow images whose file paths are contained in a data frame. So I'm going to turn this into a path object, which will allow us to sort of get all of the image files in within the path. So let's do this. Creating file data frame. So in order to use flow from data frame, we have to create one that has one column for the file paths of the images and another column for the labels for each image. So we can get the file paths by taking our image_dir, which is this nice path object, and calling the glob function on it. That allows us to specify a glob expression to search for files within the tree. So let's find all JPEG files, because I think these are all stored in JPG. So we'll search anything. That double star means you can go through directories, and then ending with something.jpg. And so this will return all files that end with JPEG in the whole recursively through the images folder. And this is actually a generator object, so we can turn it into a list just by casting it into a list like this. And you can see we now have the file path of every single image, and this is going to go into both folders and find them. You can see these are all the others, which are not dandelions. And if we go down, you can see these are the dandelion folders here. Alright, so I'm going to store this in file paths. And then to get the labels, let's look at one of these. So file paths sub0, look at the first element. It's a POSIX path object. That's the same as just a path object. And I'd like to get this value, because that's actually the label value. This would either be dandelion or other, depending on which class it's in. And the best way to extract that is to use os.path, which has a nice split function that allows you to split either a string or a path object into two parts. One is the file name, and the other is the parent directory of the file. So I don't need this part, so we're just going to take the first element of that split, and then we're going to split it again. os.path.split, and that should split off the label name away from the rest of the path. So now I want the second element, so we'll do sub1, and that will just give us the label. Alright, now I want to do this for any arbitrary file path we pass in. So what I'll do is I'll change this to x, and we'll define a lambda function that maps any x to this transformation of it. So if we pass in a file path as x, we'll get back the label name within the file path. And now I want to map this to our file paths list. So we'll map this function to file paths. And then we'll turn that map object back into a list again. And you can see we now have the labels associated with each image. And I'll call this labels. So now we have one list of file paths and one list of labels. And I'd like to create a data frame out of them. So first I'm going to turn them both into panda series. And I'll give each one a name. So we'll call the file paths file path. And we'll call the labels label. And we'll just overwrite the originals. So this one will be file paths. And this one will be labels. Alright, then once we have those two series, we're going to concatenate them together into a single image df using pandas.concat file paths and labels along axis 1, so side by side. If we look at what that looks like now, you can see this is what we want. We have the file path in one column and the label in the other. And now we're going to do our train test split. So we'll get train df and test df using the train test split function from sklearn. Pass in image df, and we'll give it a train size of 70%. And we'll keep shuffle equals true so that it'll shuffle the images around before it makes the split. And we'll give it a random state so we can reproduce the shuffle. Alright, so now we look at train df. The images have been shuffled. Now this is only 70% of the data. Test df is the other 30%. Alright, and so now we're ready to move on. So now what we're going to do is to create our generators. So the generators are going to take these data frames, and we're basically going to specify how we want to flow images from the data frames into the environment for training. So the purpose of using a generator is that if you were to load in all the images at once, now I'm not sure how big is this, 3.5 gigabytes? This wouldn't really be such a problem, but if you're working with larger image data sets, you definitely want to use a generator because you're going to run out of memory if you try to load in all the images at once. So the generator loads in a few images at a time, specified by the batch size you choose. It trains on the batch, then recycles the memory for the next batch. And so you never run out of memory doing this. Alright, so we're going to use this image data generator. You can write your own generator if you like, but we're going to use the built-in image data generator, which has a lot of nice functions for us. And we're going to create two. One will be our train generator, and one will be our test generator. So both of these, we can apply any sort of image augmentation to the images here, as well as any pre-processing. The only thing I'm going to do is rescaling. Actually, there's two things I want to do. We're going to rescale by a factor. Actually, we're not going to rescale, and here's why. Let me pull up the documentation for MobileNetV2. So MobileNet is a transfer learning model, which basically means it's already been trained. It was trained on a huge data set, usually the ImageNet data set, which had over 1,000 classes. So it's very good. These models that we'll be using are very good at extracting features from images. Very good at looking at any image and pulling out relevant information. And so it's very nice to be able to use one of these for that reason. You don't have to worry about building your own feature extractor with convolutional neural networks. You can just use one that's already been pre-trained. So if you want to use a pre-trained model, you should just check out if it needs some sort of special pre-processing. And in this case, we're going to use the pre-process input function that comes with the model. And we can specify this right inside here with pre-processing function equals that tf.keras.applications.mobilenetv2.preprocess_input. Oh, I see. We don't have to, we shouldn't call it. All right, there we go. So this is our pre-processing function, and we'll use the same thing for the test. And this will take care of all the pre-processing we need. Now the only other thing I want to do here is give this a validation split of 20%, because I want to draw the validation images from the same generator. Alright, there are our generators. And now we're going to flow from the data frames. So that's train generator dot flow from data frame. We just specify the data frame we want to flow from. This will be train df. The x column is the file path column, so that's called file path. And the y column is the label column, which I called label. Then we will give this a target size. So the target size allows us to resize all the images to be the same size. And the MobileNet model takes images of size 224 by 224 by 3. Now you can change this based on the input shape argument, but we're going to keep it the same as it was originally trained on. So we're going to resize all the images to be 224 by 224. We don't have to put the color channels here because we specify that with color mode, which will be RGB for 3 color channels. Then our class mode will be binary since we're working only with 2 classes. And we'll give it a batch size. That's like how many images do we want to load in at a time. This will also be used when we train the model, so we don't have to specify it in the fit function of the model if we specify it here. We have our batch size. We have also a shuffle. So we want to shuffle the data when we're doing the training. For the testing, we're not going to shuffle, but for the training we do. And we'll give it a seed, which is just a random state to allow it to reproduce its results. And we'll also specify a subset, which will be training. This subset argument is only used when you have a validation split. It basically specifies, do you want the 20% validation or the 80% training? In this case, we want that training data. So I'm going to copy this over, and this one is going to be validation. So it's going to draw images in the same way. Only difference is this is taking the training images, this is taking the validation images. And this we're going to store the result in train images, and this will store in val images. Now this variable might be a little misleading because this isn't actually holding the image data. It's just holding a sort of a specification for how to load the data. However, you can still pass this into the model with no problem. So that's why I call it train images. Then we'll also do our test images. This one's a little different though, because this we're going to use the test generator to flow, and we're flowing from test df instead. We also don't need a subset or a seed because we're not shuffling. We'll just keep it false. Alright, and okay, we have one issue, which is that the file paths must be strings. And what actually we have up here, these are path objects. So we're going to turn them into strings just by doing .asType string up here. Okay. Alright, and you can see it has validated the images, and you can see it found how many classes they belong to. We have 707 train images, 176 validation, and 379 test. Alright, so now we're going to download the feature extractor. So the reason I'm calling it a feature extractor is because this MobileNet application is heavily optimized for extracting features from images. So that's really the point of a convolutional neural network, is to take out, to find relevant information encoded in the spatial relationships between pixels and extract them into single features that represent something about the image. So we're going to download the feature extractor. I'll call it feature extractor. This will be our MobileNet model. This is tf.keras.applications.mobilenetv2. And we specify a few things here. One thing would be the input shape, which we'll just leave as 224 by 224 by 3, which is the default. And then include top. Actually, before we do that, I'll just do weights. We want to make sure the weights that it was trained on stay. So we're using the same ImageNet weights that It learned by looking at the original ImageNet dataset. Okay, and then we're going to specify include top equals false. This is very important. Include top means don't include the classification part of the model. So there's two parts of a CNN. There's the feature extraction part, which gets the features, and then the classification part, which uses those features to do a classification. Now, in our case, we want to build our own classification part of the model, so we're going to leave include top equals false to leave it off. However, we can also specify a pooling layer, which allows us to just put a pooling layer at the end of the model, which will have the effect of bringing the output of the model down into one dimension. So I'm going to use average pooling. We're going to need it in one dimension if we want to feed it into a dense layer. Okay, and then once we've downloaded the feature extractor, we're going to set its trainable attribute to false. So this is saying we don't want to train the feature extractor. Keep its weights static. They've already been trained on ImageNet. Just leave them the way they are. Okay, it's done, and now we will start training. So now we want to build the whole model. So we'll have our inputs, which is just going to come from the feature extractor's input, like that. Then we're going to feed the output of the feature extractor into a dense layer. So if we look at, let's look at this. If we look at feature extractor dot output, you see it outputs 1280 features. Now these are the features that it has extracted from the image. We're going to use these in a typical neural network style with two hidden layers. So I'll give it 128 activations or neurons, and I'll give it a ReLU activation function, and we'll pass in the output of the feature extractor. And I'll copy it over for a second layer, and this one will take in X, and then from the output of that we'll get the output of the model, which is the classification, also a dense layer with one value it's returning, and a sigmoid activation function. And so sigmoid will make sure that this one value takes on a value from between 0 and 1, which will serve as a probability for whether or not we have a dandelion in the image. We'll pass X into this, and we'll create the model. tf.keras.model. The inputs stay as they are, the outputs stay as they are, as we specified them. Then we'll compile the model. We'll use an atom optimizer. For loss function, we'll use binary cross entropy. And for metrics, we'll just use accuracy. I'm gonna calculate it myself. Well, not actually. I'm just gonna use the sklearn accuracy score, and I'll also use the F1 score, so we can see a more reliable metric. Okay, and then let's just print out a summary of the model. Alright, here's the model. You can see it's pretty big. There's quite a few layers in here. But we don't have to worry about that because they're not trainable. You can see that we only have 180,000 trainable parameters in the model. So now we're going to train the model, and we'll only be training the part of the model which is right here, these two layers. Actually, these three layers. The weights between these layers, so the weights between this one, the weights between this one, and the weights between this one are the ones we'll be training. So let's store the history of the fit in history and call model.fit, pass in the train images, specify some validation data, that will be our val images, and then we'll give it a number of epochs. So we'll train for 100 epochs and use a callback function, tf.keras.callbacks.early stopping, and that will allow us to monitor the validation loss. And after some patience threshold, let's say 3, that means after 3 consecutive epochs of no improvement in the validation loss, which means the model's starting to overfit, we'll stop the training and we'll restore the weights from the best epoch. So restore best weights equals true. Alright, and with GPU acceleration on, this shouldn't take very long because we're not training the original, all these weights here. Okay, and I guess we can just get the results while that happens. Not going to do too much analysis of this model. We're just going to create a set of predictions using model.predict on the test set. And because this actually returns a two-dimensional output, I'm going to squeeze it down into one dimension. Just remove that extra dummy dimension there. And then we're going to calculate the accuracy score with the sklearn accuracy score. We'll just pass in, I'll call, sorry, this is not xtest, this is test images, and I'll call this predictions. And we're going to compare predictions to the actual labels. So that's test images dot labels, and we're comparing it to predictions. Then we'll get our F1 score, which is going to again compare these two values. So F1 score is a better measure of how your model is doing between classes. If let's say our model was doing really well in one class but not so well in the other, it's not really such an issue because we don't have a class imbalance. But accuracy is, if you do have a class imbalance, accuracy is sort of prone to, is not very informative in that case. So we should hope to see something similar between these two values. We'll see. So I'll pause the video and return to it when it finishes training. Alright, so the training is complete, and you can see that the early stopping callback kicked in, and it stopped because the validation loss started going back up again. So it's restored the weights from this epoch, which was the best one. Now let's get the results over here. Alright, so actually we got an error because the problem is, if you look at, let's look at what predictions is. If we look at predictions, you can see it's actually a set of probability values for each of the images. So if a given probability is over 0.5, then we can classify as a dandelion. If it's under 0.5, then we classify as no dandelion. So what we're going to do is convert this into a basically a Boolean array where we ask, is it greater than or equal to 0.5? And that will be a true-false thing that we can then turn back into a NumPy array. Well, actually, it already is one, so let's just do as type numpy.int, and that will convert the falses to zeros and the trues to ones. So there are our actual classifications, and let's store that in predictions, and then we'll calculate these things. Alright, let's print out the accuracy. Let's display it to 2 decimal places and as a percentage. So we'll format with ACK, and we'll print out the F1 score as well. I'll display this one to 5 decimal places since it's not a percentage. And actually, since this is a percent, let's multiply it by 100. Alright, so we got an accuracy of 83.38%, so fairly good. And an F1 score of 0.832, so just about the same. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.